Welcome back to our second podcast in this course. Our topic today is off-grid systems. We are going to look at the different components that off-grid systems consist of and what their specialties are, what is available on the market, what are the differences. And as an expert, I have today with me Alessio, who works for Phocos, one of the big off-grid companies. Maybe you can introduce yourself with a few words.
Thanks for inviting me. My name is Alessio Alario. I am product manager at Phocos for AnyGrid. And I think I would quickly like to explain what we mean by AnyGrid. AnyGrid is a product line of ours, but more specifically in this context, it actually means that I deal with both off-grid systems, grid systems, and anything in between. So essentially, we also call this edge of grid, and usually inverters are somehow involved in that.
Mm-hmm. Can you give a short insight? What is a PV off-grid system for you?
A PV off-grid system is a system that is not connected to the power grid in any way. So usually in remote locations, could be to power various devices. I think we're talking mostly about smaller systems, so it might be used for industrial sensors, it might be used for powering your mobile phone, your laptop, your lighting, basic house appliances, up to, of course, there's a higher end to this, up to entire homes, businesses, and sometimes even entire villages. And off-grid simply means that there's no connection to the public grid whatsoever.
In our context, we are specifically talking about smaller PV systems, to like small PV off-grid systems to up to 5 kilowatt PV power. In that size range, what would be a classic 5 kilowatt off-grid system for you? Classic 5 kilowatt, that's starting to approach what we call residential markets. So that's typically powering an entire home. It really depends on what region in the world you're living in. Of course, different people have different power requirements. Maybe in the United States, that wouldn't quite suffice to power an entire home. In Europe, it's borderline. You can do a lot with 5 kilowatts if you choose your loads wisely. Essentially, such a system will, if we're talking off-grid, will always consist of a battery. Then some kind of a power source or multiple power sources. Obviously, we're talking mostly about PV, but there could be others like diesel or gasoline generators, fuel cells, wind power. And then we would require some kind of a charge controller to charge the battery from that power source. And then finally, if we're talking 5 kilowatts, usually there's an inverter involved. It depends on what type of loads you're using. If you're using DC loads, then you don't require an inverter. You can typically connect those loads directly to your charge controller. But if you're using AC loads, then you will need some type of an inverter to make your AC power for those. Yeah, in that size range, I would say that AC loads are quite common, right?
Absolutely, yes.
Yeah, that's
vast
like
majority. Yeah.
The normal loads that you're using in the household and that you would have typically in a household when it's grid connected, right?
Exactly, yeah.
Now that you're working for Phocos, you have quite a famous product, the AnyGrid. What is special about that one?
The AnyGrid is actually a product line. We have several, let's say, families within that range. So AnyGrid for us means usually something with an inverter and usually something that is sometimes or always connected to the grid, but it doesn't have to be. It could be a completely off-grid system as well. So within the AnyGrid family, we have the PSWH and PSWB series. The PSWH, first of all, PSW stands for pure sine wave, and the H stands for hybrid, and the B, in the case of the PSWB, stands for battery. There are some differences between those units, but both of these product lines can interface with an AC source, such as a grid or a genset. They can interface with a battery, a PV array, and loads, of course. For the PSWH, the important differences to the PSWB are that we can deal with much higher PV voltages,
which tends to make it a little bit easier to install because we can avoid having to use combiner boxes, for example. We can essentially have only 1 or 2 PV strings, whereas with the PSWB, you need more, typically 3, 4, 5 PV strings, which in turn requires a combiner box. Also, the PSWH can function with or without a battery. In fact, it can even function with only PV and loads. That's a very rare combination, but theoretically, if you have just a small AC load and you don't want to invest into a battery, you could power that directly with a PSWH from PV without requiring an AC source or a battery. But most systems use either a battery or they are connected to the grid or both.
But the special thing is that the AnyGrid, the PSWH, is like a hybrid inverter. So can you explain what that means?
Yeah, correct. Exactly. The H stands for hybrid. What that means is that we're mixing multiple power sources together and just essentially making it easier for the user to use multiple different power sources and to have the inverter take care of that for you. So hybrid usually, by our definition, means that we're mixing power sources. So in our case, that could be PV and then a further AC source, such as maybe a generator. And in that way, the PSWH, it can mix those energy sources, but you could also use it, for example, to, if you are connected to a grid, to feed into a grid as well. So there's just very many different use cases for that. We have use cases as well which have no PV whatsoever. The PSWH can be used purely as an uninterruptible power supply. So you might have like a computer farm or something like that and have batteries and maybe no PV. Then you could use the PSWH to power all of your servers, and when the grid goes down, then seamlessly you would continue operation from battery power. The switching between an AC source and off-grid mode takes about 10 milliseconds, so it's extremely fast.
And the cool thing is that you don't need an external charge controller. So it's actually combined in the AnyGrid altogether, the inverter and the charge controller.
That's right, even more than that. We have an inverter, we have a charge controller, we have a transfer relay between the grid and the load, and we have an AC charger as well. We can use the AC source, such as a generator, to charge the battery as well. And all of that in a single package, which essentially saves you a lot of work when you're installing the system, because it's an all-in-one system. You don't need to take the traditional approach of selecting a charge controller and an inverter and then maybe even an AC charger and combining those together and ensuring that they talk to each other, setting up each unit individually. That's definitely the beauty of this product. It's much easier to install, easier to use, and a lot more cost effective as well.
Yeah, that's what I also saw, that it kind of became a trend now that people rather go for hybrid inverters, like the combined charge controllers and inverters instead of the separate devices. I know Fronius is developing one now. Victron has already one. The Steka PLI is available. So just a few more models that are available in the market. Would you say that this is really like the technology to go for, or?
I would say it depends. I would say that definitely the advantages we've just discussed is lower cost, is ease of use and ease of installation. I think what still speaks for individual components, so a charge controller and inverter separately, is if you have a big mismatch between the AC power that you need and the PV power that you have. So for example, you might have a very big load, which is only running a few minutes a day, maybe a big pump or something like that. And that means you don't need a huge PV array. You might just need a few hundred watts, even though the load might be a 5 kilowatt load. And in such a case, you would have to look at whether it's actually not cheaper to buy just a very small charge controller and then a dedicated 5 kilowatt inverter, as opposed to buying an all-in-one unit, which will typically be symmetrical. You will typically have roughly the same amount of PV power that you can use as the amount of AC power that you can put out. So in the case of our PSWH, for example, we can put out 5 kilowatts in the larger units, and we can work with about 80 amps of PV current, which translates to about 4.8 kilowatts. So it's very similar. So again, if you have a big difference between your load power and your PV power, then it might be worth looking at discrete components, or if you're looking at extremely small systems.
Okay, yeah, sounds logical. Yeah, what I would think is that you are, as you said, yeah, you're more flexible when choosing the single components. You don't have it built into the case, but you can really check what you want to power and then choose the components accordingly.
Yeah, that's absolutely correct. Although because you do have a significant price advantage in the all-in-one unit, you don't necessarily need to have a perfect match between the two. So going back to my example, if you have a 5 kilowatt load and you have maybe just 2 kilowatts of PV, you're probably cheaper off by buying an all-in-one unit. Even though you're not using that extra 3 kilowatts of PV power that you could, because the all-in-one unit does tend to be quite a bit cheaper than buying the individual components. There's a lot of component duplication. There's a lot of components that you need in both an inverter and a MPPT charge controller, for example. And just by combining those two into a single one, there's a lot of overlap. So there's a lot of gain, and that translates into lower cost. So I would say rule of thumb, if your PV is half your AC power, then I think it's already worth it going for an all-in-one unit. If it's 10 to 1, then of course you're probably better off choosing discrete components, individual components.
Okay, so there are not really any other negative points besides that you might have the PV or the load side a bit bigger than you actually needed. But apart from that, there's not really a disadvantage.
It really depends on the individual devices that you're considering for your installation. You might have an advantage in self-consumption. Sometimes the discrete components have a little bit better self-consumption. Not always. It really depends on what models you're looking at. And then if redundancy is very important to you, then you might feel better if you have an inverter which is separate from a charge controller. Like that, if you have an issue with your inverter, then your batteries are still being charged from PV. Although that argument too is sometimes true, but not always, because for example, for our hybrid inverters, there is a lot of crossover between the inverter part and the PV part. But for example, the inverter can function just as a pure charge controller as well. Like you can literally just turn off the AC output, and maybe if you have a weekend home or something like that, make sure that all your loads are off. But the inverter will still run to just charge your battery. It will continue to function just like a pure charge controller while you're away.
Okay, so like protecting the battery even though it's not used.
Exactly, keeping it topped up all the time.
Okay, yeah, that's cool. So talking about the charge controller and the role it has in a PV system, we said protect the battery already. Can you sum up quickly what else the charge controller is doing in an off-grid PV system?
Sure, yeah. Exactly. The main job, obviously, which also gives its name, is to charge a battery. That in itself is not a super easy task. There's a lot of things to look out for. You need to make sure you don't overcharge a battery. You need to make sure that you charge a battery correctly. So, there's various stages in charging. There's usually a boost stage, a float stage, sometimes an equalization stage. So the charge controller needs to be capable of handling all those different voltages and currents that your battery requires to be properly charged. And by properly charged, I mean not only getting your battery full, but making sure that when it's not being used so much that it can be in a float stage almost indefinitely. So we need to make sure that the battery is fully charged, but also make sure that we increase the life expectancy by making sure that we're being conservative in the voltages that we're giving to the battery if it's for long term.
So to break it down and maybe explain it a bit like non-technical, I always like to compare a battery to a water bucket that you fill with water, and the water would be the energy you put into the battery. And then you mentioned the float charge. That would be the first charging stage?
That's the lowest voltage, correct. Yeah, that's the one.
So that's where you begin to charge.
It's not where you begin to charge, it's where actually you finish charging. Typically, you go through various charging stages, and the last stage is always float. That's essentially, let's just say it's the default voltage for the battery. I would say it's the voltage where the battery can stay at safely forever.
essentially, without aging too much. I think if we're comparing this to water, which I do like that to make that comparison as well, maybe the water tank, which is the battery in this case, isn't a bucket, but rather a balloon. And the charge controller is supposed to fill that balloon with water, and it's supposed to make sure it never pops, which would be overcharging. It's supposed to make sure that it's never empty. And when you're charging it up, you want to make sure the balloon is really full, so it's really tight, but you don't want to keep it that way for many days or many weeks or months. You need to let some water out to make sure that it doesn't stretch too thin. I think that's the best comparison I could make there.
Yeah, and then the charge controller kind of, when you're still in the stage where you're pushing a lot of energy into it until the balloon reaches a decent size, you would just put more energy into it, and then when you reach like the size when the balloon is close to bursting, you're kind of reducing the energy input. That's right.
Yeah, you're essentially controlling the water tap that is feeding the water into the balloon. You're either increasing or decreasing the volume, and maybe to bring this over to some other functions of the charge controller, one is also to prevent deep discharge. So as you may know, a lot of virtually all batteries are not allowed to be discharged to 0 volts. They always have a safe window, a minimum and a maximum battery voltage, and the charge controller is supposed to ensure that the minimum battery voltage is that the loads essentially never discharge the battery below that minimum battery voltage. So to make sure the balloon essentially is never out of water. And the charge controller does this by controlling your load. It can switch off your DC loads. If you're using an inverter, the inverter should do the same at a certain battery voltage. So it monitors the battery voltage, and when it decides that the voltage is becoming too low, essentially this will happen every time that you're taking more energy out of the system than you're putting in. So maybe at night, or maybe if we're talking about PV during maybe snowy days, or maybe the monsoon season or whatever, you're taking more energy out of the system than you're putting in. So the battery, being that water balloon, that buffer of energy, will drop in voltage, and the charge controller simply has to prevent that from happening too much, because otherwise, if you discharge a lead acid battery to 0 volts, you can essentially destroy it in a couple days.
What about lithium batteries?
Lithium batteries are easier in some respects and more complex in others. Easier in that they're actually simpler to charge. There tend to be only 2 stages, maximum 3 charging stages, whereas for lead you tend to have 3 to 5 stages, depending on the different products and manufacturers. Lithium makes it a little bit easier to use because they already have some electronics typically built in the form of a battery management system, so also known as a BMS. This is an additional electronic circuitry directly integrated into the battery, which monitors the battery. And essentially, if you were to connect a load directly to that battery without a charge controller, if it's a good battery, you shouldn't be able to deep discharge it, because the battery management system would simply shut down your load. It's actually, it fulfills some of the similar functionality as a charge controller does while discharging.
But you still shouldn't do it.
Yeah, you shouldn't do it. It's
not
always
to give bad ideas.
No. It's BMS should be your last measure of protection. The battery management system is there to protect your battery from an unsafe situation, from overheating, from overvoltage, undervoltage, making sure that all the cells are balanced. It has a lot of things to do, but you shouldn't think that just because you have a BMS, you don't require a charge controller at all. That's definitely not true.
Okay, good. Yeah. So, but definitely when deciding for a charge controller, you should check if it's compatible to the battery type you selected, like if it can charge lithium or lead batteries, depending on what you chose.
Correct. You want to see that the battery type is supported, that your minimum and maximum battery voltage are supported, and that you have that you don't exceed the maximum current rating of the battery. That's important as well.
Okay. Then there's different types of charge controllers. When we now think we are not using such a hybrid inverter where the charge controller is already built in, but if we go for the single charge controller and inverter, which I think is in many countries, and especially smaller off-grid systems, still the way to go, just because of availability. So what choice do I have? What types of charge controllers are there?
Well, there's two fundamental groups in PV charge controllers. Those are the PWM and the MPPT charge controllers. They both have their advantages and drawbacks. One is not better than the other, but one may be better suited than the other in certain systems or scenarios. And then within the MPPT, we have some more categories. I don't want to go into too much detail there, but essentially there's buck, there's boost, there's buck boost. Just essentially whether you can use a higher PV voltage than a battery, a lower, or both.
Let's maybe start at the beginning. Let's look at the MPPT charge controller. What does MPPT stand for?
Okay. Actually, if you don't mind, I would prefer with PWM because it's so much simpler.
Yeah.
And because I think if we understand PWM, we can understand the advantages of MPPT. PWM controllers are much older than MPPT as well. The first charge controllers in the early 2000s, late 90s tended, or at least commercially available ones, tended to be PWM. Essentially, a PWM charge controller. You can, going back to our tap water balloon example, it's as if you have control of the tap, and when the balloon is starting to become too full because you're charging it, you turn the tap on and off very quickly. And you turn it on and off quickly so that you're putting exactly as much energy into the balloon or water into the balloon as you are taking out of it with your loads. So to bring this back to electricity, you want to essentially make sure that the amount of power that you're putting into your battery is the same when the battery's full as the power you're taking out. That's the only way you're not going to overcharge your battery. If you just keep powering your battery and your load power is lower than that, then your battery will just keep rising in voltage, and at some point it will just, well, if things go very bad, it will explode, but otherwise it will just overheat and vent and things like that. So a PWM charge controller is essentially like a very fast light switch. It cannot convert anything. It can just turn on and off. So essentially it's as if you connected your PV modules directly to the battery, had a switch between, and would control the switch to make sure that you're keeping the battery voltage in the safe zone.
So that's where the name comes from, PWM?
Yes, pulse width modulation, yes. And it's a glorified term of just saying switching on and off, yes.
Okay, that's easy. So are there any special requirements then? Switching on and off doesn't sound like you have much control over the actual system. So is there anything that needs to be considered when going for a PWM?
Right, like I said, PWM charge control cannot convert. So essentially you need to match your PV modules very closely to the battery voltage. So if you're dealing with 12 volt batteries, typically we work with crystalline PV modules. Those are by far the most popular ones. You would take a 36 cell PV module, and that roughly matches the battery voltage. In reality, it's actually slightly higher, and it needs to be. The PV voltage must always be a little bit higher with a PWM charge controller so that you can successfully fill up the battery even when temperatures get warm. The warmer temperatures get, the lower the PV voltage tends to be. So essentially, for a 12 volt system, you need 36 cell modules, and for a 24 volt system, it's twice that, it's 72 cell modules. And that's where things get a little bit complicated because the, let's say, most available modules worldwide tend to be the 60 cell modules. There's some, there's different types of PV modules. Some of them have a lot more cells, but the most common ones are 60 cells, and then 72 cells, and then 36 cells. Now, the problem is, of course, if you have a slightly bigger system with several kilowatts, you want to use the cheapest PV modules, right? And the problem is using those 60 cell PV modules with a 12 volt system and a PWM charge controller will give you an efficiency of about half. So you will only be able to use about half of that PV power. Why? Because the PWM charge control cannot convert the higher PV voltage down to the battery. It can only switch on and off. And 60 cell modules tend to be just a little bit too low voltage for a 24 volt system.
In the online webinars, we compared the voltage with the force that pushes the energy through the wire or through the conductor. So that's maybe how you can imagine it, the force that the PV modules then push into the battery or into the charge controller is just not enough to get on the level that the battery needs.
Right, for the 60 cell, correct, yes. Yeah, it can actually, it's a delicate balance. If your PV voltage is too low, and if your charge controller wouldn't prevent this from happening, then actually the PV modules would be heated up by the battery. So the battery would actually discharge into the PV modules.
Also, it's flowing back then, because the voltage level is lower there.
Correct.
You can, water flowing down a hill.
Current always flows towards the lower voltage. Exactly.
Okay. Oh, that's interesting. Yeah. So.
But of course, the charge controller is supposed to prevent that from happening. It's one of the important functions of a charge controller, because otherwise every night your battery would be heating up the PV modules and discharging itself, which of course would not be a good idea. So the charge controller will notice that and will simply disconnect the PV modules from the battery if that risks happening.
Okay, yeah, good to know. So another protection measurement. All right, so for PWM, it's simple technology, switching on and off. But you need a certain size of modules, and you need to make sure that you have not only the correct voltage level, but also higher voltage level than your battery voltage in order to be able to correctly charge the battery.
That's right. PWM charge controllers are the simplest ones out there. They tend to be the cheapest as well because of their simplicity. And as is the case with many simple things, is they tend to last the longest. The components that are used inside PWM charge controllers tend to age less quickly than MPPTs.
That's a good information, I think, especially for off-grid systems that are installed in very remote areas. You don't want to go back to have your components fixed all the time. So if it's long-lasting, you install it once and then it just runs.
And also PWM tends to perform better for many years at hotter temperatures.
Okay, so for deserts or...
Exactly, yeah. The high temperatures, extremely high temperatures, I'm talking like 40, 45 degrees centigrade and more, tend to make the electrolytic capacitors in inverters and MPPT charge controllers age more quickly. And PWM charge controllers just don't have those, or certainly not as many. And so they will tend to be a little bit more robust. This also explains why, for example, telecom is still one of the biggest markets for large PWM charge controllers, whereas almost everybody else has switched to MPPT, as we'll explain in a moment why they did that. But for telecom, it's really not that important to be super efficient. It's more important to make sure that the system remains up and running for 20, 30, 40 years, preferably without maintenance. And PWM charge controllers are capable of that.
Okay, interesting. Yeah. Good. You mentioned MPPT is different. So what is different about the MPPT charge controllers?
Yeah, so like I said, the PWM is essentially just a glorified light switch. So you cannot, let's say you have a high battery or a high PV voltage of, let's say 30 volts, and you have a battery of 12 volts. Then a PWM charge controller will just connect your PV modules to your battery and then disconnect it again if necessary, many thousand times a second. And essentially, if you look at the voltage of your PV modules, it will be 30 volts, then 12 volts, 30 volts, 12 volts, etc. There's nothing in between. And an MPPT charge controller can work in between that. And that's really where all of the advantages come from. So sticking with that example, if I have a 30 volt PV module and a 12 volt battery, then for simplicity's sake, let's just say the PV voltage is twice as high as the battery voltage. In this case, the PWM charge controller will only be able to use half of your PV potential. The MPPT will actually convert the higher PV voltage to the lower battery voltage. So this is a real DC converter. You have 30 volts input on your PV side and 12 volts output on your battery side. So essentially, you're transferring the voltage and you're turning it into current. So if you're halving your voltage, right, from PV, it means you're doubling your current. And that, in a sense, if we're comparing that to the same system with a PWM charge controller, means you have twice the efficiency.
Oh, wow, that's a lot.
In this example, yes. It's not always the case, but yeah.
Yeah, but conversion for me sounds a lot like losses.
That's right. Yeah, there's always losses involved. Typically, conversion losses are somewhere between 2-3% in the best case, and in the worst case, maybe 10%, or in some edge cases, maybe even a little bit more. Also, the bigger the difference is between the two voltages, the more losses you tend to have.
So even in an MPPT charge controller, let's say you're capable of working with 200 volts on the PV side and you have only a 12 volt battery, then you will still tend to have a poor efficiency, big losses, because there's such a big difference between the two voltages.
Okay, so it's not like just use whatever, it's still you need to like select components and match them together.
Yes, and there's influence you can take to make the system as efficient as possible. That's right. But I think one of the biggest advantages of MPPT is not only that it can, essentially what we've talked about so far is that you're using the incorrect PV modules with the battery, or the cheapest ones in some cases. That's obviously one big advantage of MPPT, that we can do that and still be efficient.
So we are not bound to the 60 cell modules.
That's right.
With the MPPT.
We're not bound to the 36 and 72 cell modules.
Okay,
that's
so
right.
We can use whatever module we get.
Exactly, yeah. And we tend to be able to put many modules in series to reach higher voltages. And we have a lot more flexibility in how we configure our PV array. I think one of the biggest advantages of MPPT is that, well, as we've learned now, the bigger the difference in voltage between the PV modules and the battery, the more conversion makes sense. Because the more losses you would have with a PWM charge controller. And of course, this can happen if you're using modules which aren't necessarily suited for your battery. But I think almost as important is looking at seasons. In many countries, we have a big difference between winter and summer seasons. And in winter, the temperatures might be significantly lower than in summer. At the same time, in winter, we tend not to have nearly as much PV power. There's many countries where you have 5 times as much power during the summer, on average per day, coming from the same PV array as you do in the winter. And of course, if you're in an off-grid system, it's very important to be able to provide roughly the same amount of power throughout the whole year. And that means that we need to optimize the worst months. So in Europe, for example, that would tend to be around December, January, when it's cold outside, it might be snowing. We need to do everything we can to increase our PV output. And an MPPT charge controller can really go a long way there, because in the winter, like I said before, when it's cold, the PV module voltage goes up. The battery voltage stays about the same. So the difference between the two increases. And so MPPT is even more beneficial in the winter. And incidentally, that's when we need every last watt of power, because in the winter is when we have the least solar power. So anytime the weather is bad, we don't have a lot of sunshine, that's when MPPT will make an even more significant difference in efficiency over a PWM.
And what does MPPT stand for?
Maximum power point tracking. So it's looking at what the maximum watt output of your PV module is by essentially varying the voltage and the current. So it just makes sure that your PV module is operating at its best possible potential. And a PWM charge controller cannot do that. It can only not take power or essentially connect the PV modules so run at the same voltage as the battery. MPPT can control the voltage of the PV modules completely independently from the battery.
And that's what makes MPPT charge controllers more efficient despite of the conversion losses, because it can get right the exact maximum power point from the PV modules. Okay. So what would you look out for when deciding for an inverter? When would you take an MPPT?
A charge controller.
Yeah, sorry. When would you take an MPPT charge controller?
Well, I've kind of mentioned those points. When the PV voltage and the battery voltage are significantly different, right? Because I want to use 60 cell modules on a 24 volt or on a 12 volt system, or because I'm working with a very big system, so I want to have a higher PV voltage because it means I have less strings, I don't need combiner boxes, things like that. So whenever the PV voltage is very different from the battery voltage, that's when we almost definitely need an MPPT. And then also, like I said, when we have a strong seasonality, we have a big difference between summer and winter, and we really need to optimize for the winter, then MPPT charge controllers will also help. Also, if you have a lot of cloudy or diffuse weather, so, like monsoon season, for example, or foggy skies, things like that, again, MPPT will make a big difference there. What really speaks for PWM is if you have the 36 cell modules for your 12 volt batteries, or twice that for the 24 volt batteries, of course, then
MPPT is less required, but is still usually a good idea. In PWM, really, I think the great advantage of PWM is the price. As I mentioned before, PWM tends to be a lot cheaper than MPPT. It tends to be very reliable. And there's some edge cases where PWM can, and this is very rare, and you really need to know what you're doing, but PWM can be more efficient than MPPT. If you have exactly the right modules, you have the right batteries, and the right temperature. But because you can't control it, it really only happens, if you have just the right weather, etc.
Okay, so for a small system where I really look at the price of components, I should check if a PWM would work for my application, and then if not, I would then only look at an MPPT.
Right. Yeah.
Okay. Cool. Good. So now charge controller is sorted. Then we need an inverter if we want to connect AC loads. What choices of inverters do we have for a 5 kilowatt off-grid PV system?
Well, here too we have kind of two categories. We have pure sine wave and modified sine wave inverters. Essentially, you probably know what a sine wave looks like. It's what comes out of your electric outlet at your home, certainly in most countries. And a pure sine wave inverter tries to make a perfect sine wave. So it tries to be as close as possible to what you're used to from the grid if you have a stable grid.
So the sine wave kind of describes the quality of the AC power.
That's right. It's the shape of your voltage, essentially. Exactly. And a modified sine wave essentially is a way for inverter manufacturers to reduce cost of the inverters at the cost of signal quality. So the quality of your AC signal will be much worse with a modified sine wave inverter. And that can have various effects. But first and foremost, price is obviously a big deciding factor between those two. And modified sine wave inverters tend to be significantly cheaper than pure sine wave inverters.
When would it be relevant? Do I need top quality sine wave all the time? Or are there occasions when I can say I'd rather go for the cheaper option?
It depends what loads you're using. If you're using resistive loads, so for example a heater, which is essentially just a resistor, then a heater will not care if you're using a pure sine wave or not. It will work almost as well on a modified sine wave inverter. If you're working with more sensitive electronics or anything that has motors inside, like like a cordless drill, like a pump, like a compressor for your fridge, anything that has an AC motor inside, if you're using a bad modified sine wave inverter, then not only will the efficiency decrease, but you will also tend to heat up those motors. So of course that's bad for their life expectancy. And also for sensitive electronics, modified sine wave inverters will introduce noise. So electrical noise, but also a noise that you can hear. If you're using it, for example, in an audio system, then chances are with a modified sine wave, the system will sound a lot worse than it does on a pure sine wave. So nowadays, only for very small and simple systems would I recommend modified sine wave. Otherwise, if you're unsure, or if you know that you're going to power a whole home, like a whole residential home, then it really doesn't make sense to go with modified sine wave. Certainly not with the larger inverters. Maybe for 100, 200, 300 watts, a modified sine wave will do the trick. If all you're doing is maybe powering a soldering iron or just something that's heating, which again is like a resistive load. Certainly anything above 1 kilowatt, I would go with a pure sine wave inverter.
What about the classic appliances that you would have in a household that you would be powering with an off-grid system, like a TV, lamps, charging your phone? Is it relevant for that?
There's no easy answer to that. It depends on the power supply of whatever you're using. Strictly speaking, if your main goal is to charge your laptop, your phone, and some lighting, then you shouldn't be using an inverter at all. You should be doing everything in DC. You will have a much more efficient system and probably a cheaper system as well. But of course, if you're powering your whole home, you have a lot more loads, right? You have the whole kitchen and some other loads. Then it depends. Again, it depends on the quality of the power supplies of whatever loads you're using. The thing is, with a pure sine wave inverter, you're always on the safe side. you know that you're essentially providing the power the way your loads were intended. All of your loads are made for a grid. So if you're replicating a grid perfectly, then that's great. Then you're not going to damage your loads. As soon as you go too far away from that, there's always a risk that you'll damage your loads, or that at least they will wear prematurely. So I would consider phones, laptops, and things like that in the sensitive electronics category, and I would definitely recommend using a pure sine wave inverter for those.
Okay. Then looking at the different inverters that are available, there's like the very small ones, which I think are the ones that sometimes have the modified sine wave, sometimes the real one. But they are like those very small boxes, just off-grid inverters, where you sometimes have the plug outlet right on the inverter already.
Right, yes.
And then there's bigger ones, like where you don't have the plug anymore, but you have to connect everything through the cables, and you can connect it to the DB board and things like that. What are the differences between those, like the basic version and the bigger ones?
Well, the one you already pointed out is definitely size. Very small inverters, like 500 watts or below, sometimes 1 kilowatt or below, tend to have the socket integrated into the inverter. And they tend to be mobile, which means that they don't need to necessarily be permanently mounted to a wall or something. So these are very practical for very, very small systems, or for camping and things like that, and where it's a great benefit actually that they're mobile. As you go up in power, the devices tend to get a lot more heavy, so it makes less sense to make them portable. And as soon as you get into the permanently installed larger systems, I would say like 2-3 kilowatts and above, then you don't even want to have an electric outlet on those inverters anymore, because usually in a home, if you look at your home, and if you are connected to the grid, you'll see that there's a box in your home, right, where you have all of your fuses and things like that. And that's essentially what you would connect to with a permanently installed inverter, which is larger, which doesn't have an electric outlet. It doesn't need to have an outlet because it will connect into a distribution. And there you will have multiple fuses and different parts of your, I'll call it a microgrid, what essentially you're trying to create. Then you don't want an outlet. But if you have just 2-3 loads or something to power, and if you're talking about less than 1 kilowatt, then it tends to be quite practical to have an electrical outlet. Also, there's a big difference sometimes in quality, but also certainly in the amount of settings you have. For these smaller inverters, you tend to have maybe just one setting, which would be 50 or 60 hertz. Sometimes you can take influence on how low the inverter is allowed to discharge the battery before disconnecting. Remembering the low voltage disconnect functionality of charge controllers, and the same of inverters. But essentially that's pretty much all you can do in terms of settings for the small inverters. And for the large ones, there's so much more. There's especially if we're talking about these hybrid systems, there is like priority settings. There you can modify the AC output voltage, usually, of course the frequency as well. You can define how low to discharge your battery and how to charge your battery. There's various bypass modes and things like that. There's just so much more functionality in a hybrid inverter that you want, but that you also need to be able to take influence with settings on. So the small ones tend to be very simple. I would say cheap and cheerful, and good for very small applications. But as soon as you get into the bigger applications, you tend to get a bit more professional as well, and you'll want to have a lot more settings to be able to modify.
So the criteria would be, like, if you're looking at whether you should get a simple small inverter or a bigger one, you mentioned mobility. If you have to move the system around, or if you want to have it like fixed, installed, connected to the grid that's already installed in your house. You mentioned the price, like the budget of the system, and the amount of settings that you need, or the flexibility you want to have with the different settings. That's
right, yeah. And I would say the robustness as well, because you'll tend to have some of these smaller inverters, like in an extreme case, maybe the ones that are made for a 12-volt car cigarette lighter outlet. Those are not designed to run 24/7. They're designed to run maybe half an hour, maybe an hour or something, just to power your laptop for a while. But the bigger inverters that tend to be installed permanently, those are designed usually for everyday 24/7 operation, continuous.
So when buying an inverter, you should look that it's really a solar inverter, that it's made for running permanently and not only like 2-hour emergency power or something. Yeah. Okay. Yeah, that's important to know. What is the limit that those simple inverters have, like the size limit? Until what power capacity do they go up?
With simple, do you mean the modified sine wave, or just the smaller individual inverters?
The smaller individual.
Okay. I would say up to about 3 kilowatts. Usually even I would say up to, somewhere between 2 to 3 kilowatts. You tend to have the standalone inverters, which often have a electrical outlet, and anything above 3 kilowatts tends to be the more permanently installed and wired inverters.
Yeah, makes sense, because then your batteries are also bigger, and
of course,
that's not a size you want to carry around then.
You're not going to be able to carry a 5 kilowatt system around with you. You can install it in a vehicle, of course, but you're going to, I think the batteries alone will weigh about 50 kilos or more, so it's not something you're going to put in your camping bag.
Okay, yeah, no, makes sense. All right. What about a monitoring system? You were talking about different settings, and the more complex inverters, I can imagine you could monitor the performance. Are there monitoring systems for off-grid inverters?
For the small ones, typically not, at least none that I'm aware of, because monitoring obviously costs some money. You need to set up the system, and you need to typically have some kind of a data connection to your system. And that's really not economical for very small systems of just a few hundred watts. As you get into let's say roughly 2-3 kilowatts and above, as you start getting more into these permanently installed systems, regardless of whether they're actually installed in a mobile building or whether they're installed in a big truck or something, that tends to be more serious equipment. And for that equipment, many manufacturers offer some kind of a monitoring solution. In the case of Phocos, there's various methods to do that. We have some local monitoring, which is actually implemented for free. So you can, on the PSWH series, for example, of inverter chargers, you can hook up your phone to the inverter and you can see what it's doing without investing any extra money, because the Bluetooth is already implemented into the inverter. Then you can also extract the data through a USB stick. Because we have some internal memory in the inverters. That too is free in a sense, because you only need to look at it if there's a reason to, for example, if you have an issue or if you want to just control what's happened over the last month or something. And then I would say the most elaborate form of monitoring is the remote monitoring, where you have a real connection to the internet typically, and that you can really monitor your system from afar. So if you're on the go, you can just, take out your phone and see what your system is doing at home. Or if it's a professional installation, you can monitor that. For telecom, for example, they always want to monitor their system because they can't send somebody out to check up on the system, once a week. It's just much too expensive. So in the case of Phocos, for that we have the AnyBridge, which we're bringing out, which allows you to connect your hybrid inverters to Wi-Fi or Ethernet, and therefore to the internet. And then you have an online portal where you can log in and see exactly what your system's doing and look at past data and have everything nicely presented to you in the form of charts.
Okay, so to sum that up, we have two options. We have when you're standing in front of the inverter, you can hook up on the Bluetooth with your phone.
Local monitoring, yeah.
Local monitoring, or connect a USB flash to get the data, but that you need to be with the inverter. And then we have the remote monitoring that works through the internet, uploading the data, which we can then see. Yeah.
Exactly, yeah.
But I would say there's the price difference.
There's price,
a bit bigger.
Price and infrastructure, because what good is a remote monitoring system if you don't have an internet connection? And the only time you're going to have an internet connection is if if you're working usually with bigger systems. You tend to not have. Let's go back to our solar home system example from the start, where we just really want to have some lighting, maybe charge up a laptop and things like that. And maybe if you're in a small hut, like a hunting hut or a weekend hut or something like that, there might not be any telephone wires at all. There might be no way to connect to the internet. So of course, remote monitoring will simply not be possible without investing a whole bunch of money into infrastructure.
And not really needed, I would assume. Is it?
Probably not needed either, yeah. I mean, if you have a super critical sensor or something, oil and gas or whatever, then, they will have the capital to invest. But if it's just for a vacation home, well, then usually you don't need a remote monitoring system.
Okay, so if there's like no critical loads or infrastructure that you're powering, it is fine. I mean, it's inconvenient when the system is not working, but it wouldn't cause any risk or danger if the system doesn't work, and then you can just go and fix it when you see it doesn't work.
That's right.
But for like critical things like telecommunication or critical infrastructure, you would want to know what's going on all the time, and that's why you would have then a remote monitoring. Especially
like critical infrastructure where the technicians that know how to analyze the system are not always at the site. So you might have obviously a hospital, for example, would be critical infrastructure. But if somebody's there at the hospital 24/7 that is knowledgeable of the PV system and that can handle it, then strictly speaking, you don't need remote monitoring. But if you just have a technician which will come if there's an issue, then of course remote monitoring is very valuable, because maybe that technician can analyze the system remotely before even going to the site.
Okay, yeah. So again, it's checking your application if it's necessary, and then checking the budget if you really want it.
That's right, yeah.
Okay. One last question on the inverters. When deciding for an inverter, and there's if you ever checked where to buy inverters, you will see there's a huge variety out there, and it's hard to take a decision when you don't really know all the products. As an expert, what would you recommend? What is or are there any quality criteria where you say this should definitely be included in the inverter, or this is something where you can look out for?
Yeah, absolutely. I think one of the first goes for pretty much any consumer device is that you tend to be better off by taking brands, because of course brands work with reputation, and a brand is less likely to bring an unsatisfactory product to market, because they know that would cause bad reputation to that brand. So buying no name equipment is possible, but you need to know what you're getting into, and you should be able to dive deeply into what you're getting, so that you're not you don't end up with bad surprises. So brand is one thing. Then, as I mentioned, the pure sine wave versus modified sine wave, depending on your application. Then, of course, there is the efficiency. That's a very important point as well. Typical inverters will have efficiencies somewhere between 80 and 95, 96%. So that efficiency can make a big difference. But especially in small systems, what I would rate almost more important than efficiency is the standby consumption, or the self-consumption. So that is how much power the inverter will consume, even if it's not powering any loads, if it's just switched on. So essentially, for example, a self-consumption of 10 watts would tend to be a very good figure for an inverter of, let's say, 500 watts or something like that, or 1 kilowatt. It sounds like very little. But if you multiply that up and you do 10 watts times 24 hours, that's 240 watt hours per day. And the inverter hasn't powered anything yet. So you need to be able to have a PV array of at least 50 to 100 watts only to power the inverter. You haven't powered any loads yet. So that's really something to take into account. And that's why, for example, I recommend for people that are living in energy constrained areas, so in areas where you might have an off-grid system, it tends to be a good idea to power as much as possible from DC. So maybe your lighting, maybe if you have one, your television, just the things that tend to run for many hours a day.
So that you don't have to switch on the inverter.
That's right, exactly. Okay. Leave the inverter turned off, maybe just use it in your kitchen, or just, maybe for some tools. And when you don't use them, just turn off the inverter. Like that, it doesn't have any self-consumption. And that can really make the total system cost much cheaper because you need a lot less PV and batteries to power just the inverter.
Yeah, and it is realistic, because when you look at the normal use of a system, I would say the majority is having light in the evenings and at night.
Right, yeah.
That's kind of running the longest. And then I think the actual AC loads that would require an inverter are used for a shorter period of time.
That's right.
I don't know, you charge your laptop and then it's full after 2 hours or something.
Yeah.
So then you can switch it off again. That's a good hint. All right. I would assume the tips you gave on the brand are also applicable for the selection of the charge controller.
Of course, yeah. For the same reasons, yeah.
Okay, yeah. I think then we discussed the most important points on inverters, what to look out for, and how to make a choice. One last topic maybe, opposed to DC coupled systems, the ones that we discussed now, where we have the charge controller charging and discharging the battery, there's also AC coupled systems that instead of the charge controller use the two different inverters. Would you say that an AC coupled system is also something we can use for a 5 kilowatt off-grid system?
Yeah, as you mentioned, DC coupled typically means that the PV power or the charge controller is connected to the battery. And AC coupled means that we tend to combine an off-grid inverter charger with a grid inverter. And that might sound a little bit counterintuitive in an off-grid system. Why would I be using a grid inverter in an off-grid system? Well, essentially you're creating your own small microgrid, and a grid inverter, if your off-grid inverter is compatible with it, then that grid inverter, you connect it to the same AC power lines as you're using to power your loads. But that inverter, instead of consuming power, will actually feed power from PV through your off-grid inverter into the battery. So essentially you're charging, that's why it's called AC coupled, because you're coupling your PV power on the AC side. There's a few things that you need to consider for that. First of all, if you compare this to these all-in-one systems, such as the AnyGrid PSWH I've mentioned, the hybrid inverter, those, like I said, one of the advantages of those systems is that they're very simple. You just plug in your PV, your battery, your AC, change a handful of settings and you're set, you're good to go. With a DC coupled system, it can get a little bit more complicated because, of course, you have a separate charge controller and a separate inverter. So you need to make sure that they kind of work together well. You need to make sure that your low voltage disconnect, for example, is about the same on both of them, or just take that into account. So the complexity is a little bit higher. For AC coupled systems, the complexity gets a lot higher. First of all, we need an off-grid inverter which is bidirectional, so which is capable not only of sending power to your loads, but also of receiving power from the grid inverter, the first requirement. And second, we need to be able to control how much power is flowing. And that's where things get quite complicated, because we need to tell the grid inverter when to stop delivering power, because maybe the battery's full and the loads don't need all of that power. We need to do things like change the voltage or the frequency of the AC signal. So you need to really know what you're doing there. You need to know how to set up your off-grid inverter to be able to not only receive the energy from the grid inverter, but also to control it. And then you also need to take into account what happens when your battery voltage is low. And then you might turn off your AC loads, right? But if you turn off your AC loads, you've also turned off your grid inverter, so you can't charge your battery anymore. So you're kind of in a checkmate scenario there. So there's a lot of things to consider for AC coupling. And the last issue might be that because it takes some time for the grid inverter to react to the commands that the off-grid inverter is giving it, you could end up with some oscillations and things like that. Just suffice to say that you really need to know what you're doing. And I would always recommend choosing a combination of off-grid inverter and grid inverter which has been successfully tested together before.
So like manufacturers that produce both the grid-tied inverter and the off-grid inverter, or that have been approved by the manufacturers and tested in the field. That's right, yeah. I think the former, it's rare to find manufacturers which make good off-grid inverters and grid inverters.
But certainly there's a lot more off-grid inverter manufacturers that have tested specific grid inverters to work well with their equipment, and that's what I would recommend. I really there's maybe two advantages I see for AC coupling. First is that in very large systems, the efficiency may be higher. Certainly the efficiency from PV to AC directly is the highest.
So when you have like daytime loads,
correct,
powering a factory or something,
exactly, or a mine or something that's working, that's working during the day. That's just the highest efficiency. And for very large systems, you can build like a distributed mini grid. So you might have like a large central battery in a village connected to multiple off-grid inverters, and then again multiple PV arrays which could be distributed throughout the village. I think those are the two real use cases for AC coupling. Certainly only, in my opinion, relevant for system sizes well beyond 5 kilowatts. I would start thinking about AC coupling at maybe 20, 30 kilowatts, something like that.
Okay, yeah, that would have been my feeling as well. So the DC coupling is like a lot easier, also for like not so experienced installers.
Correct, yes.
There's still a lot to do wrong, but like not
much less
as complicated as for the AC coupled. So starting with that for the smaller systems, and then only when like complicated technology is needed, going for an AC coupled system.
For a DC coupled system, even if you're using an inverter, you don't need to know very much about AC. You tend to need to know quite a bit about DC and PV and things like that, but you don't need to know much about power factors, sine waves, and things like that, inductive and capacitive loads, all those things that you need to deal with if you're dealing with AC. An AC coupled system, you need to know all that in order for that system to be stable and to run successfully.
Okay, yeah. One important note that nobody is confused by DC coupled and AC coupled. So DC coupled, the coupling just refers to the connections within the system. It doesn't mean that there's only DC loads. So you can, as we said with the inverter, AC loads can also be connected to that, and you can power AC loads from a DC coupled system. It's just that the electricity is not converted into AC. And then for the AC coupled, it also refers again to the connections. And as you said, the grid-tied inverter takes the PV power and converts it right into AC, and then that is used in the system. And then AC loads are connected. But opposed to a DC coupled, I think DC loads can't be powered with the AC coupled system, can they?
Yeah, they could actually, yeah. The AC or DC coupling always refers to how your PV is connected to your battery, essentially. With AC coupled, again, it's a grid inverter via AC through an off-grid inverter into the battery. So there's a few conversions happening there. And a DC coupled system tends to be PV through some kind of a charge controller directly to the battery. You could theoretically have an AC coupled system and simply run your loads off the battery in DC. You could theoretically do that.
Yeah, but nobody really does.
I don't think I've ever heard of the system.
No, it would be weird.
Yeah.
Okay. Yeah, I think this is a lot of information on the systems, and I think we could have talked for another hour. But this was already a lot of input. So yeah, thank you very much. If there are any questions, you can look at the other modules and the other learning material, or consult the learning guides in the online learning portal. Then thank you, Alessio, for being here and sharing your knowledge. It was super interesting. And yeah, thank you.
Thank you for having me, and I hope this was useful to anybody who listened. Thank you.